welcome to the Examples in Code Generation Integration for HIL and SIL application. Today's outline will introduce ourselves a little bit and give some context for the material we'll be going over, as well as examining 3 case studies that we've prepared for this presentation, starting with a D-Space transmission model, a Samsung SDI battery model, and a parallel HEV model that was done with IPG. And then of course we'll be wrapping up everything with our summary notes. To give you a little bit of a sense of what we aim to do here at MapleSoft, we provide tools that have been designed to address engineering challenges by allowing you to tackle complex systems using system-level modeling. These tools provide design insights early in the development process, helping to reduce your time to market, and can uncover challenges that normally are discovered when the hardware prototype stages, and thus enabling you to manage your development budget effectively. Modeling and development often includes many subsystems from a variety of engineering domains that need to work together. This results in subsystems interactions that are key to the overall performance. And of course, once you start bringing these systems together, there oftentimes are problems that start to arise, and debugging and a lot of engineering time is spent on how to properly manage these. When we start taking a look at the MapleSoft solution to this, we look at this from a system level and multi-domain approach, where we can develop our virtual prototyping by doing a lot of modeling and simulation using our toolchain. Then we develop into how you analyze your model, actually see where you can optimize your model and explore the workspace, see what kind of sensitivity or if your model is sensitive, and do sensitivity analysis, as well as understand things like inverse kinematics and inverse dynamics for your particular model. Of course, afterwards you'll be wanting to integrate your findings and your overall model into other platforms, and here's where we can introduce things like real-time code generation, as well as exports to the FMI, FMU standards, Simulink S functions, and National Instrument or D-Space connectors. In today's presentation, we'll be mainly focusing on the third aspect, which is the solution development and integration using our MapleSim connectors, and showing those examples of code generation. Let's take a look at our first case study, which is the automatic transmission model that we did with D-Space. To give you a bit of a sense of what the idea was for this model, we want to create an automatic transmission that was going to be used with a hardware-in-the-loop testing. Here we see a representative image of the overall model, and we'll be mainly focusing on the transmission component from the model that we developed. Inside the model, we'll be wanting to include features such as the gear structure, multiple clutch systems, as well as a torque converter. Then we want to be able to simply export that using one of our templates that will automatically generate code for us. In this case, we'll be using the FMU template and connecting that into the D-Space Galexio environment and being able to run with the rest of the models that are there to provide the overall vehicle modeling environment. Let's actually jump into MapleSim and see what this looks like. So here we can see the gearbox model for the transmission that we have. This transmission model is accompanied by a simple connection with an engine representation of our vehicle that we're going to be using, as well as the longitudinal dynamics for this vehicle model. The reason why we've included some of these other features, such as the vehicle dynamics, the engine model, and also a driver model, is that we can do our virtual prototyping in MapleSim before we export to FMU, C code, or an S function. The model that we've actually developed is inside this subsystem here, the transmission block, and we can connect to each of these external components using our signal information for instance, like the torque that we're outputting, the wheel speed for the 2 wheels that we'll be driving, as well as information that's going to be coming in from our main controller, such as the gear shifter, and what the engine's actually going to be doing, so the engine torque, and be able to communicate with the engine speed back. Going into the transmission model itself, we can see that there are quite a few components that are modeled within the system. We can see that we take that signal input that relates to the engine torque and the engine speed and communicate those both inward and outward, and directly connect that to something that is physically modeled as the rotational shaft to our torque converter. We have our torque converter model represented here. The torque converter is then connected to our grouping that we've indicated here with our gearbox, where we can see that there are several clutches and planetary gears that are combined together to create the overall gear ratio and shifting that we want in our model. These clutches are then controlled based off of the table data that we can see here, where the output results for each of the clutches then drive the clutch response to engage one clutch system or to release a clutch system. The automatic portion is contained within this subsystem, which will allow the engine RPM to rise to a certain threshold and then shift the gears appropriately. That gear shifting information is then passed down through the gear table, or the clutch table, to then change the gears accordingly. At the exterior portion of our gearbox, we've also included a park lock system that allows us to hold the vehicle in a park position, as well as the differential that allows the rear wheels or front wheels, in this case actually, to be driven. So that way we can connect the driven wheels with the wheel speed and wheel torque that are then communicated to whatever external system is on our target platform. I've already ran the simulation here to give you a set of results so that we can see our probed information here. And I'll expand. And by allowing the MapleSim model to include the vehicle dynamics and as well as the engine components in our testing, we can do some preliminary runs on our transmission model to get a good sense of whether or not the transmission model is behaving the way we expect it to before exporting that. So at the top left-hand corner here, we can see the vehicle speed, both the desired and measured response, and we can see an excellent agreement between the two. We can take a look at the signal information that's going to be used for the engine model to see how that's behaving in our system. And we can look at how the overall gears are being shifted over time while they're trying to follow this drive cycle. Other information can also be tracked, such as the speed of the different clutches. And we can look at what kind of variance we're getting and to see if there's any issues in our model response before we hand anything on. Returning to the presentation, we can get a sense of where this will go in our overall big picture. Now that we have a transmission model, that model then will be integrated with DSpace Coalexio platform, which then is connected to the rest of the hardware in the loop that we're actually going to be testing. And the model that we're providing is the transmission component, but the vehicle itself has also been modeled. You can see even an image of the vehicle here, along with the environment that the vehicle will be driving in. Now, in real-time applications, we want to be able to get a sense that we have some headroom whenever we are performing our analysis. One of the key factors is to make sure that we're always making our real-time benchmark. In this case, our limit was 1 millisecond step sizes. And as you can see here, that our average computation time was only 90 microseconds. And our maximum peaks that occurred at the most dynamic ranges of the simulation were 0.21 milliseconds, so well below our threshold. This allowed the model to work quite effectively in the hardware in the loop real-time application where they were testing their electronic stability controllers. Let's take a look at our second case study. This was a modeling and validation of a large battery pack for Samsung SDI. The challenge here was that Samsung was looking for a different approach to how they can do some of their battery testing and monitoring. The challenge that they're faced with is that a lot of the battery systems are very, very expensive to do a significant number of tests on. We can see here in our image on the right-hand side, each one of these battery cells often need to be provided into a temperature-controlled chamber, and running the tests with these temperature-controlled chambers and the chambers themselves can be costly in the orders of millions of dollars, in fact. These tests are then normally connected to some kind of controller system that is used to run the tests. Perhaps there are several of these in parallel. And of course, at the end of the chain will be some kind of operator looking at the overall results, doing data analysis and number crunching. The objective here is to replace a lot of the expensive equipment that's going to be used in the testing with a MapleSim model, but yet maintain a high degree of fidelity. Samsung was able to provide quite a bit of experimental results, as they already had a lot of the equipment there, and they can perform some of the testing themselves. As we can see, here's an example screenshot of some of the data that they were able to provide. We were then able to take that information and do some curve fitting with the model that was developed using our battery technology. And we can see an excellent agreement with root mean square error of 0.005. So we have, and even in the curve, you can see that the fitting is quite excellent. What we wanted to do with that battery data was then combine all of those individual cells into a large pack. There was 144 cells that were going to be used in this hardware in the loop testing. And the overall pack needed to include information that provided balancing current information, and then provided externally information on the state of health, the state of charge, and the voltage for each one of those 144 cells. The results of this was that the model was able to be exported, in this case using a Simulink XS function. The 144 cell pack was simulated with 1 millisecond fixed step solver that was already pre-packaged. And an example we have here of a simulation that ran for, the simulation time was 5 hours, so 18,000 second simulation time was computed on a computer using an Intel i5, and the average execution time for each one of those step sizes was 55 microseconds. So quite well below our 1 millisecond threshold that we need to achieve. We'll take a look at our third case study. In this case study, we had a full hybrid electric vehicle that we worked on with IPG Automotive. To give you a sense of how this integrates, this is an example where we are starting to combine the skills and development that we had in the previous two examples, as well as expanding on that. We can see here in this hybrid electric vehicle that we have an engine block that is connected with our motor generator, some power electronics, and a battery system. The motor generator and engine will then be coupled together in a parallel configuration to our CVT, and then output it to our differential driving our driven wheels. We can see this in the actual MapleSim model. So returning to MapleSim, we can see here that we use a similar approach where the middle subsystem is the HEV powertrain that we're actually modeling. Again, we've included a drive cycle and controller to be able to test our HEV powertrain in MapleSim before exporting it. And we've used the similar longitudinal vehicle dynamics to provide a load to the overall powertrain. In this case, we're also interested in things like the fuel rate, which gives us some insight on the fuel economy or miles per gallon. Expanding the powertrain model, we can see that the information from the accelerator pedal and brake pedal are provided into our rule-based torque controller, where this controller then can distribute the overall torque demand either to the electrical motor or the internal combustion engine. And the output from those two driven shafts can be combined again where we can see the combined torque driving the CVT. That is then exported. The overall shaft torque and speed can be then connected to the final drive and differential that are then coupled together with the driven wheels. In this case, the transmission controller that controls the CVT is designed to run the engine at its optimal point, known as the brake specific fuel consumption optimal point, or BSFC. And the electrical motor is designed as a small powering assist motor system, where when we expand this, we can see a motor model for our power system, as well as power electronics with our PID controller for our power electronics. Included in this system model is a nickel metal hydride battery, as well as some protection measures that will prevent the battery from being fully charged or overcharged or fully discharged, allowing the battery to always operate in a nominal range. Collectively, this hybrid powertrain then is used then to drive the overall vehicle. And again, we can see some simulated results. If I expand our results window here, we can see here that once again in the top left-hand corner, I've included a bit of a drive cycle as well as measured results. In this case, you'll notice that there's a region where the model, it doesn't track the overall speed at the very bottom. And the reason for that discrepancy is that this vehicle model does not include the hydraulic brakes, rather just the regenerative braking component that comes as part of the hybrid powertrain. The hydraulic brakes will be included when this powertrain is added to the rest of the vehicle system. We can also see how our battery is behaving. In this case, with this fairly light load that's on the vehicle, there's enough energy overhead that the battery is able to be charged as part of the control strategy used. And we can see how the different torque responses are occurring. So for the internal combustion engine, we can see there's different torque load as the engine is trying to match the desired torque that's loaded on it. And similarly, the electric motor has a significant range of torque that it must provide and accommodate to be mirrored with the internal combustion engine. We're able to track properties such as the engine speed, overall energy for the powertrain that's being used, whether or not we're charging the battery mainly or discharging it. In this case, as we can see, our SOC is generally climbing. That means that our recharge process is mainly happening. So in this case, we're using a negative sign to indicate recharging. And we can get a good sense of what the overall behavior of the powertrain is going to be well before we export this. Let's take a look at how the exporting process actually can happen in this powertrain model. So we see here our subsystem. We have included several different templates for the code generation, FMU generation, NI connectivity, as well as Simulink block connectors. Each of these templates behave very similar to one another. I'm going to open up an example that I have already attached to the model, as you can see here on the left-hand side. So in this case, I'm expanding the C code generation template. I have a little bit of a preview window that allows me to view my MapleSim model. So I can see the powertrain MapleSim model in my preview window here to make sure that I'm selecting the right one. Load up that subsystem, and what MapleSim is doing is it's working with Maple as the underlying engine to automatically determine what the underlying equations are and identify what my inputs are, my outputs, and any of the key parameters that are used in the powertrain. I can toggle on and off. As we can see in this example, there are some parameters that I have disabled, as well as some parameters that I have enabled for exporting. This allows the user to provide access to any of these parameters if they want, or they can disable them so that nobody can change them once they've generated their code. Our code also will automatically include any of the fixed step solvers if you would like. And so I can, for instance, pick my Euler fixed step solver, and I can leave it as whatever the initial step size is that I'm applying here. Of course, you can always vary these to your specific target needs. Specify my target location, and then it's simply a matter of clicking Generate C code. The MapleSim model will then be compiled or analyzed and then compiled, if you would like, for applications like FMI or S functions. If you want to just leave it as C code, we can also just export directly as C code like I've done here. And I can see in my temporary folder, that's the target location that I provided, and we can see that I've just generated this C file. This code is all standalone code, so you no longer need to be connected to any Maple or MapleSim server or access licensing, and the code is automatically generated as royalty-free code. To give you a sense of what some of the other templates look like, I'll open up the Simulink block connector template, and you can see that the overall structure is quite similar to the C code template. And I'll just scroll down. As you can see that it'll load the inputs and outputs much the same way, as well as the parameters. And in this case, with the Simulink block connector, you can decide whether or not you want to include our own fixed step solver, or if you want to use Simulink solvers. That allows you to integrate nicely with your variable step solver as well. And the process to export is quite the same. You can simply click Generate S function, so you can create your C code version for your S function without compiling. This allows you to compile in the specific environment that you'll be targeting towards once you have the file there. Or if the computer that you're currently running on also includes MATLAB Simulink installed and you have the compiler already that you want to use, you can simply click Generate and compile your S function right from the template. And so you can see how we can develop our subsystem, and all we need to do is specify our IOs. And within the subsystem, the MapleSim model can include multi-domain system modeling, from the electrical to mechanical, overall control structure, and be able to relate the physics of what's happening in the powertrain out to the driven wheels that are connected as the output side, and how the driver model will be connecting with the accelerator pedal and brake information to control the overall powertrain. Returning to the PowerPoint presentation, we can see what the overall results look like. The performance we were able to get allowed the full vehicle model to achieve better than real-time performance, which was quite important for us in our target application, as this model was designed to allow for optimization and sensitivity analysis. And oftentimes in optimization applications, we need to be able to run models much faster than real time, especially for large models like we see here with powertrains or vehicles, since we'll be running the optimization with hundreds, if not thousands of different variations and configurations over the analysis time period for that model. And this enabled the optimization process to determine to a high degree of accuracy what some of the optimal parameters are, and the sensitivity analysis to give us a good insight into what parameters are actually significantly affecting our overall system without the limitations of having large computational overhead that will be commonplace with other modeling approaches. Overall, the approach is to provide system level and multi-domain modeling where we have 3 different groups. This is done through simulation, design exploration, and control and verification. What we focused on today was mainly the control and verification process, where we're exporting our real-time code to our particular environment, whether it's through FMI or FMUs, Simulink S function connectors, directly to our application like NI or DSpace, or if we're just going to use C code. Maple and MapleSim work together to provide you this level of functionality, where we can see that there's a great deal of expanded material for either our add-ons, where we have our driveline, battery, and tire library, as well as many others, along with any of your connectivity to your currently existing toolchain through MATLAB Simulink connectors, LabVIEW, C-Code, or if you're developing with JMeg and web page interfacing. In summary, we explored a number of examples in the system level modeling and code generation for real-time application. Each of these models had the MapleSim generate the optimized code, allowing for high-fidelity dynamic modeling. And MapleSim is able to provide you with the best shot to achieve your high-fidelity and real-time performance execution that you're looking for.